Okay, so today it's my great pleasure to introduce Wieslawa Niziol from Jussieu, who will speak about hidden structures on the Rham cohomology of P-adic analytic varieties.
Thank you. I would like to thank the organizers for the invitation to speak here. It's always a pleasure to be in Chicago. So what I want to tell you about to present is it's a survey type of a talk. We are looking at the Rham cohomology of P-adic analytic varieties, and we are looking at the structures which appear of this cohomology. So usually you have the usual Hodge filtration, just as in the classical case, but because you are in arithmetic situation, you also get data coming from reduction, not P, so you have Frobenius and monodromy. And in algebraic setup, we know that this data altogether satisfies certain stability conditions. So we try to discuss it. And in the analytic setup, the stability fails, and we are trying to figure out whether you still have reasonable restrictions on this data. And these are partial results we have with some collaborators. I will mention their names later, and that's what I will discuss at the very end. Okay, but most of the talk will be a survey of what we know so far. So I'm going to simplify the notation, and I'm going to assume that we are working over a finite extension of P-adic. So P-adic is the completion of rationals with respect to P-adic valuation. And I'm going to look at finite extensions of P-adic numbers for simplicity, but for specialists, maybe you have to keep in mind we can actually do much better here. So I'm going to denote by OK the ring of integers and small k the residue field, which is perfect, so finite actually. And C would be what is often denoted by CP, which is the completion of the algebraic closure of QP, and this is algebraically closed. So we are going to denote by GK the Galois group of C over QP bar over. So much for the notation. I think that will be enough. So let's look at the first case I want to discuss, which is that of algebraic varieties and their cohomologies. So I will look for simplicity into smooth and proper varieties over K. And to such a variety, we can associate two cohomology theories. So we can look at the Rham cohomology. So this is cohomology theory built from algebraic differential forms, algebraic varieties here. And then we can look at the cohomology. That's another object we will be interested in. So we extend the coefficients to C, to CP. And now we have Galois group acting here. So we have Galois group, so GK acting on the total cohomology group. These are finite ground vector spaces over QP, and these are finite ground vector spaces over K. So a little bit of remark about the classical case here. So if X is defined over the real numbers, algebraic variety over real numbers, we have comparison theorems. So a cohomology, now this is an extension to complex numbers with QP coefficients, is an analog of Betty cohomology, as probably you heard many times. Extended to QP. And then we have a period isomorphism between the Rham cohomology and this Betty cohomology with C coefficients. So that's a classical picture. So I just wanted to mention these two cohomology theories that we have associated in with the varieties in this situation. Now I want to sketch a history which refers to the study of these two objects and the relationship between them. So the first result I want to mention is state around 67. I try to check this dates and they should be more or less correct. So he formulated a conjecture which is known now as Hodge state comparison theorem, a comparison conjecture. There should exist a fuzzy isomorphism. So you look at a cohomology. This has an option. This action is highly non-trivial, but we are saying that if we base change our coefficients to C, then this action is going to be trivialized. The value action here. So this was the object we're interested in. This action is going to be trivialized. And moreover, the multiplicity, so what we will get are just cyclotomic characters, and the multiplicities will be controlled by the Hodge groups of the varieties. So more specifically here, we have a decomposition called Hodge state decomposition. So this is GK equivariant. And I think the twist right here. These are twists by cyclotomic characters. So cyclotomic character, this is the character you obtain from acting on the towers of P roots of unity. This is what Tate formulated in our case. And now what did Tate prove? So this is okay. He proved it for abelian varieties. So this was an indication that we can test that is correct, and we have to wait quite a bit for future. So he also was asking, maybe I should put this as a question. He was mostly interested in the algebraic varieties, but he was asking whether this is also true for abeloids, which are proper. So if you want to, maybe I should say, rigid and analytic. So analytic abelian varieties. So that was one thing which he asked in his article. So let me mention how it looks for abelian varieties for H1, only one which matters. So we erase an abelian variety. Then we have Hodge decomposition into two pieces. And I should have here this one. And this is Galois equivariant. Okay, so there was no progress for a while on this question. And then we have Fontaine-Massey first inclination that something can be done. And an idea how to attack this conjecture in general. But the proof they presented, they published, was for work for projective varieties. I don't remember anymore why they needed projective, but P had to, the main thing was that P had to be large with respect to the dimension of X. So this is what we now call the Fontaine-Laffey range, or something related to that. And what he was using was, they were using what is still in applications. Now you see it with symptomic methods for attacking this. So what is this? So here we study In this method, we study P-adic nearby cycles, and I will mention maybe a little bit more later. The differential forms. So this method was successful and extended later by the Japanese school. Actually, was successful in proving some of these conjectures, but then kind of went quiet. But later it turned out that actually it's very easy to adopt this method to rigid analytic varieties, and since the rigid analytic varieties now have a revival, then this method is still with us, and it's actually very efficient. So this was not a very, it was not, I mean, still a lot of cases, but not a general theorem. The general proof is due to 4 things, and actually not much later. And 4 things uses, so he can prove it, he can prove, so CHT is okay, but in fact also for what he calls, okay, he doesn't call it, now we call it maybe almost proper varieties. So we allow open varieties but which have reasonable compactification. And he also did, and this was substantially different from, for example, this method, that he was able to do coefficients in a good way. You can do coefficients in the symptomic method, but it's not a very general theory. But he actually, especially in fact, the good reduction case, he was very, it was very powerful method. So this is the method he used. We call it almost mathematics, if you like, almost Attali extensions. And this is what is used very often these days. And this in fact goes back. So what Frobenius did, he took the almost mathematics which was developed by Tate in dimension 0, and he extended it to higher dimensions. So the relative case. And in our minds, this almost mathematics, in those days anyways, we like to think about this, that it replaced the resolution of singularities in this characteristic, which we didn't have and still don't have. And at that time, in fact, we didn't even have alterations yet, although alterations are a little bit of it is included already in these papers. So you can use this almost Attali extensions theory to control singularities if you do it well. Okay, so this is what I wanted to mention about the history of this Hodge decomposition here. And the second thing I wanted to mention, I don't know how to call it, so maybe I should have called this one here. Second. So we have Hodge decomposition, but also if we look at the Rham cohomology of our variety, then it's equipped with the Hodge filtration. So Hodge filtration. And how do we define it? So here we can be naive and we can define it just as the image of the H cohomology in degree n of the truncated Rham complex in the Rham cohomology of degree x, which is degree n, which is the Rham cohomology of the total complex.
You're going to put the on. Sorry, on that.
And here, yes. Thanks. So what do we know about this? Here we know that the Hodge Rham spectral sequence generates a D1. It generates a D1. A D1. Let me write this sequence maybe. So here we are in the case of algebraic varieties over QP. So you may wonder how this was proved. And the generation actually follows from this Hodge decomposition. But this was not the first proof of this. There was another algebraic proof presented earlier by Lucy. So we have algebraic proofs of this kind of statements. Okay, so this is the Hodge filtration and the Hodge decomposition for algebraic varieties. But now I want to discuss fine structures, which come from the fact that we can reduce, so we can get more by reduction mod P. Okay, so let's discuss. So reduction mod P. So we take our equations, we reduce them mod P, and if we are mod P, then we have action of the Frobenius, which maps. Yes, okay. So let me draw a diagram. So in the special case of good reduction, so I have a scheme that I want. No, I don't want good reduction, sorry. I'm going to take semi-stable reduction. So this curly X is a semi-stable scheme over OK. So by semi-stable, I mean that if you look at the divisor, a special divisor over small k here, then it's a normal crossing divisor, but I also allow horizontal divisors which totally form against crossing divisors. So we allow both horizontal and vertical divisors. And then if we look at the generic fiber, our X is the generic fiber of the scheme. Then you can attach to this the Rham data. Let's say the Rham cohomology integrity of X. But you can also attach to it what we call semi-stable data, which will be associated to this reduction. Which will be what we call Hiodo-Kato cohomology of X. So Hiodo-Kato cohomology here is basically the Rham cohomology, but it carries extra structures. So it has Frobenius on it, and it has monodromy, and there is this relation between them. So let me maybe just mention a word. What is this object? It's supposed to be an analog of the Force structures in this setup. So we defined it as the cohomology, crystalline cohomology, the very crystalline cohomology of the special fiber with respect to small k. We call it sometimes OL. And there is some log structure, never mind. Here is log structure. The important thing is that crystalline cohomology is a good cohomology of the special fiber, kind of like the Rham. And it has Frobenius here now because we're in characteristic piece of the factoriality. But this thing here is it's a tangent vector which kind of is sticking out of your variety, and this tangent vector allows you to do monodromy. So that's why you get this monodromy. So this tangent vector kind of remembers that you have an equal characteristic actually the relation. And there is also an isomorphism, so something called Hiodo-Kato isomorphism. Between this Hiodo-Kato cohomology and the Rham cohomology, but I didn't mention this, but they have different coefficients, so I always consider this rationally. And this crystalline cohomology has now coefficients. It's a finite Rham vector spaces over the fraction field of these vectors, which is just F in my notation. So you have to tensor this over F with K and then you get an isomorphism. So the structures were defined in a paper by Hyodo, and so basically we have what they are telling us that in a semi-stable reduction case, you can put F linear structure in a Rham cohomology, and this F linear structure carries Frobenius and monodromy. So that's a lot of new structures of magnetic energy. So then people started to wonder, okay, we have these structures. What can we say about the relationship between these operators? So between the filtration and the Frobenius and monodromy, etc. So the abstract theory was developed by Fontaine and Nielsen. So it all was progressing very slowly, and it's called filtered phi modules, so phi for Frobenius. So the idea was the following: we define an abstract theory of filtered phi modules, then we try to characterize the phi modules which come from geometry in this kind of way. So what can we say about these structures? So first, the first one is the easy step, right? So we define object D, which consists of DST type, the Rham type, and this isomorphism, which kind of encodes this data. So I will say it in words. So this one carries Hodge filtration, is finite rank over K. This one is finite rank over F and carries Frobenius and monodromy. And there is a base change isomorphism from this to this. That's the data. Okay, now the second question was how to characterize the B's which come from geometry. So for example, from semi-stable varieties. Okay, so what in the end happened was that Fontaine defined what we now understand the stability condition in the sense of invariant theory, in fact. So let me mention this. This actually is reasonably simple to describe. So this is called weakly admissible. So now we don't even say weakly, but let me say weakly admissible here for historical reason. If we look at two numbers, so this concerns the slope of the Frobenius and TH is the slope of the Hodge filtration. So we look at the determinant of the Frobenius, look at this valuation at P, and here we take direct sum of the dimensions of the graded pieces for the Hodge filtration, and we weigh it. And the conditions here for weakly admissible state, so we have two, that TND is equal to THD. So if you think about polygons, these are the endpoints are the same. And then the second is that Tn prime is larger than image D prime for any sub-object with all the structures inside T. So here we say that Newton, this is the slopes of the Frobenius is about Hodge. So this is very simple kind of combinatorial description, right? Combinatorial condition. And it's actually insane that we didn't have a proof until quite recently. We didn't have a proof of the weakly admissibility of the Rham cohomology just from this combinatorial data. So in this case of conformacy, in this Fontaine-Lafayette case. In fact, one of the first things they prove is that actually Fontaine does the same in Fontaine-Lafayette case, that if P is large and you take the Rham cohomology, just from the Rham data, you can prove that this holds, right? But in general, we were not able to do that. So,
Can I add something?
Yeah.
So here, like the DSP depends on choice of a semi-stable reduction, a posterior distance.
yeah, that's right. No. Yeah, it doesn't depend on it. So if you have this D ion modular object, you can associate to it what we call VST of D, which is Galois representation. And this is defined. I keep in mind that this doesn't have to be finite dimensional actually, in general it's not. And this is defined by looking at DST, listing it by a ring of periods which Fontaine introduced. I will not describe it, but it's one of the period rings of Fontaine. And then we take the elements in the F0 part of the Rham object extended to the Rham. So this doesn't have to be finite dimensional finite Rham. And D is called admissible if it is. So if dimension over QP of this representation associated with D is the same as the dimension over K of D Rham. And again, it took a few years before we realized this theorem of Colmes and Fontaine that weakly admissible implies admissible. So we knew that if D is admissible, then it's weakly admissible, but not the other way around.
So a historical question. Was it clear right from the beginning that that conjecture was the right thing to make?
You mean the weakly admissible implies admissible?
Yeah. Or was it just like it's necessary, and could you do some dimension counts? I mean, I'm not quite sure how believed it was before it was proved.
I think people believe this is correct. I mean the fact, yeah, okay. Well, I don't know. I think we believe this was correct, yes. But not that anyone had a proof until they proof. Kind of strange because it's very simple to prove in the case that the Rham cohomology is actually weakly admissible in the case of Fontaine-Lafayette, but in general it's not possible.
I think Fontaine-Lafayette theory gave that. I think before it was proved in general, the fact that it was true in the Fontaine-Lafayette case was somehow strong.
Yeah, I was going to say that when Frank was asking the question, but then I thought, I mean, everything goes wrong beyond Fontaine-Lafayette. So many other things go wrong beyond Fontaine-Lafayette theory that, yeah, but maybe rationally, it was an indication. Okay, so we know that these two conditions are the same. And going back to our question about the Rham cohomology being weakly admissible, so we have a theorem now, Suji, around 98, proved that the Rham cohomology of varieties with semi-stable reduction the ones I described there, is weakly admissible. Weakly admissible. And in fact, if you look at the associated representation to this Rham data, let me write them just DN, for example, such a variety, then this is a cohomology of this variety as a Galois representation. But again, does not. But in fact, it does not what he proved. So he didn't have a separate proof that this cohomology is weakly admissible. He proves first this, So then we know that the D object here is admissible, and then we know it's weakly admissible. We didn't have a separate proof of that. Okay. So let me just mention a remark here. So I was talking about semi-stable varieties with semi-stable reduction. You may wonder what happens in general. What happens for X over K, any value. Can be open, it can be even singular. So we know now that the data which the Rham cohomology fits into, it's the same P-adic object as before, the Rham object, the comparison, but there is also residual action of Galois groups. So residual action. So residual action of the Galois group. So the idea is the following. Well, we don't have a semi-stable reduction, but if you are a smooth variety, you may wonder whether there is always potentially semi-stable reduction, right? If there were potentially semi-stable reduction, then this small representation here just remembers how far you have to go in the extension to actually get a semi-stable reduction. I should just mention, I said these are the same objects that are not quite, because this object now is defined over C-breve, which is the Witt vectors fraction of the Witt vectors of K bar. And this again comes from the fact that you have a potentially semi-stable reduction, not semi-stable reduction. So this isomorphism has to be over, the base change here has to be over C. So you have to tensor over C. But it all works very well, and there is a whole number of people who work on this kind of theorems for the last 20 years or more, and so we understand the situation very well in the algebraic setup. So another remark I want to make is that I mentioned that these conditions which are listed here are kind of semi-stability conditions, but in fact you can make it very precise. So this weakly admissible conditions are kind of semi-stability conditions. And this is for the group GLM. You can even change your group to other reductive groups. And if you do that, you get a theory of P-adic period domains. If you look at moduli spaces of some objects, so you fix for moduli spaces, you fix your Frobenius data here, and you vary the Hodge filtration, and you get a flag variety. And then from this flag variety, you extract the semi-stable locus, with a semi-stability condition. So you get this P-adic period domain, so for example, as reference space. This is an example period domain, and this was studied. This under cohomology, these objects under P-adic cohomology, so Analytic, were studied in the book of that Orlik and Rappaport. And in fact, quite a bit of this story happened here in Chicago. Before some of the people in the audience were born. Long ago. Okay. So now I pass to analytic varieties. When we understand things much, I mean, our understanding is much worse. But I am going to start with proper varieties, when in fact the story is very similar to the algebraic story, although not that we knew that before, maybe. So let me start with the first situation. So we have X over K is proper and smooth. And the slogan here should be that similar, so P-adic Hodge if you like, or these hidden structures are similar to algebraic setup. Algebraic setup. Okay, so maybe first let me just mention some examples here. I already mentioned abelians, right? For this kind of varieties. So we have abelians, abelian analytic varieties. And so a few others maybe. Okay, let's put this here as a generic fiber of non-algebraic deformations of abelian varieties of K-free surfaces. And there is also an analog of the Hodge surface, and it has the same problems. That is, it also has it's an example of situation in which the Hodge symmetry fails. But maybe surprisingly in our setup, in the P-adic setup, we actually have some kind of coherent theory of cohomological theory of these objects. So let me mention first results, and this is not so long ago, but if mathematics were moving a little bit slower than we before some people. Recently in this field we're going really fast. So Hodge around 2011 proved that so the first theorem concerning rigid analytic P-adic cohomologies, that a cohomology is actually of finite Rham, a finitely generated ZP module, and vanishes when you would expect, so for twice the dimension. Okay, then we have also abstract decomposition, like the one I mentioned, conjectured by Tate. So I'm assuming here I come from my case, so I actually do have the composition. So if I extend my coefficients to C, I get a splitting into Hodge pieces. So we have the composition, and this implies, as in the case of foldings, that the Hodge-Rham scatter sequence is a D1. So it looks all very similar, and the proof of the method of proof is a generalization, fast generalization of almost the Paris stations, really. So what Jussieu proved, what Frobenius was not able to prove, is something called almost purity, which in fact does allow you to forget about singularities in many situations. So Frobenius didn't have this powerful theorem. That allowed Jussieu to actually simplify many of Frobenius' arguments and do work only on the generic fiber and actually have a really nice theorem. So that was the powerful. And you probably take that okay. So when we start with a variety like over there, you can again associate these D objects in any degree is the Rham data. And DST, we get DST, which has from here the cutoff. The Rham, which is the Rham with the Hodge filtration, which has nice degeneration of the Rham spectral property. And here the kata isomorphism, and you have this residual action of the Galois group. Now I should explain what these things are, because we are on the generic fiber, right? So the Rham cohomology is the usual object, which we know what it is. But this object has to be defined locally. So eta locally, the origin analytic variety by the word of Temkin Arton as a semi-stable model. And once it has a semi-stable model, you can just use the crystalline Fiaducato cohomology and induce Frobenius and filtration. So you have a finite module here with the usual properties. And Fiaducato isomorphism is defined in a similar way, and like this coming from taking these alterations. So you can associate this data, and then a valid question is this still weakly admissible, or what is it? It's the same question, but what kind of structures we get here? So we have in filtered, we are still in filtered fine modules, right? But what properties the structures have? So we have a theorem that in the proper case, so X is proper and smooth, because we can associate these structures to any X, doesn't have to be, sorry, okay, let me assume it's smooth, but it doesn't have to be proper. The smoothness here is related to this étale property. So if you have a smooth variety, you need to localize just étale locally to get semi-stable models. If this is not smooth, you would have to do something like H topology or something. So the theorem, and this is our work, the different years. So we proved that these structures are still, so when X is smooth and proper, that these are weakly admissible. And also, that means that you can look at the associated Galois representation, and this is going to be the cohomology of the geometric cohomology of the Galois action. And our proof of this fact doesn't. So we don't use homozeta theory. Well, let me just say that this is very simple. But also here in this proof, we actually prove we do prove that these guys are weakly admissible before we prove that, or at least at the same time. So we don't prove this and then deduce the weak admissibility. We prove the weakly admissibility. So the technology has improved enough in the last 30 years or so that we can actually prove this kind of results now without going through Galois representations. Okay, so let me mention what happens in a more general setup. So we go outside of proper, still smooth, but not proper. So the X is smooth, but not proper in general. So what are the standard examples? So we look at the first objects we looked at were strong varieties. So for example, the Driffert space. So Driffert space, which is just Pn over C side minus all the hyperplanes defined over the face. So in dimension one, we just take P1 and you extract K rational points. So for Stein varieties, what can we say? So maybe I start with very simple examples. So let's look at examples. What are we talking about here? So as I mentioned, the cohomology mediated, and the cohomology of such a variety is now not finite Rham in general, not finite Rham. So if X is the affine space of dimension B, then what we get is that HI. Okay, I'm going to replace a tal by pro tal because that's what we can do. In this case, we can do more, but in general, pro tal. So for pro tal cohomology, remember that you don't just allow finite covers, but you allow also infinite covers. So we take pro tal cohomology of XC here for a space, and we put twists, and what we get is differential forms, not kernel of the Rham differential from the Rham complex. So I just wanted to put this formula because we see that what we are getting is actually huge, right? So these are not finite Rham vector spaces at all. But this is a very simple example. In general, you have a mixture of the classical theory and this kind of analytic theory coming from the Rham complex. And the classical theory behaves just like in the usual situation, the classical part, but it's the analytic part that is more difficult to understand. So let me look at X being the torus, another example, over K. And then we get exact sequence. So we get a filtration on the pro-étal cohomology. And here we have a classical object, so similar to the usual cohomology. So this is degree I, okay? So we have vector space generated by symbols. So these are the logs of the coordinate functions. Generated this way. And the point is that this is what you think the classical, this is the usual, that's the usual shape of classical cohomology. But here you get this analytic part, which is again the summing part. So you get so that's the usual shape of pro-étal cohomology. I want to give you one example because in this one more example, in these two examples, the classical part here is finite Rham, and there was 0 because the Rham cohomology, usual étal cohomology, algebraic étal cohomology of algebraic affine space is 0, so that's we get 0. But here, if X is the Dirichlet space, I denote that I have a notation. I will just write this way. So Dirichlet space of dimension B, 1. So Dirichlet of plane. Then this classical part now is actually also big. So we have H1 tau. Then we have Steinberg representation, which should be dual, I think. And here we get the functions, homomorphic functions, not C. And this is smooth Steinberg. So we have locally constant functions on the boundary of the Dirichlet half plane with values pp. Okay, so you can even the classical part here is becoming infinite. So what can you say about the Rham data in this case? So to say anything coherent, we actually decided to pass to the Fontaine curve. So let me just mention what we do. So the Fontaine curve makes this Frobenius and filtration, hot filtration data very kind of easy to handle. So this is a vibration filtered by modules and the Fontaine curve. So how do you think about Fontaine curve? I will be noted by FF. So let's just do it very simply. So it's built from an affine piece and a point at infinity. So I'm going to think about this, and the functions on the affine piece are given by the period ring BE of Fontaine. So with this physical ideal domain. And that was kind of the beginning of the whole story here. So this is the Fontaine point. And P-adic varieties. B Chris plus or B plus or B phi equal 1. And at infinity, if we look at the stock of functions completed at infinity, then we get B Rham plus another ring of Fontaine. So we have glued this BE with B Rham plus somehow into a curve. And so this is the algebraic story. There is also an analytic story. Then you can study vector bundles on this Fontaine curve. And again, the theory due to Candoya Liu, we know that we can talk about it in the algebraic or analytic setup. And if you look at the vector bundle, you can associate to it a slope. The usual way. And we have classifications of vector bundles on the Fontaine curve. We know that they kind of behave like the curve is a little bit of genus 0 and a lot of genus 0 and a little bit of genus 1. We have had the Narasima theory here. And for us, the point is that if we start with this data of DST and D Rham, and I will forget the Galois action. So just the Rham structure, P-adic structures, so Frobenius structures, and I. With such data, you can associate a vector bundle on the Fontaine curve. So basically, Frobenius data gives you something on the whole curve, vector bundle of the whole curve, and the filtration on the Rham cohomology modifies your vector bundle at infinity and gives you associated vector bundle. So maybe we just mention H0 outside the infinity.
This is before you know it's weak admissible.
Before I know it's weakly admissible, yes. I don't know anything yet. So H0 of ED is given by DST, and so BST phi equal 1 and n equals 0. And the point, if I look at D and I pass to infinity, I get F0 of the Rham, and so the Rham plus of the Rham maybe. So this Frobenius of filtration data goes at the infinity, and Frobenius is the cause of it. And what is interesting now that this functor I spoke before, VST, is just now to kind of guess from the of this description I gave above, that VST of V now can be computed as H0 on the whole curve of this vector bundle. So it's the curve encodes very nicely all these structures. So what kind of objects we get as these cohomologies of vector bundles here. So this is what is called now Banach converse spaces. So these are objects which have a plus or minus part which is QP vector space. So that is, you can add or subtract QP vector space to finite rank C vector space. Okay, so why I'm mentioning this? Because the theorem that I want to state here at the very end is that if my analytic variety, so if X is small, we would like it to mean that it just means that all the Rham cohomologies are of finite rank. But we cannot prove it in that generality. So I will give an example of what it means to be small. Then, if you look at the data dix and you take the associated vector bundle, then this is acyclic. So what does it mean? It means that equivalently, so these are equivalent, that or H1 on the far quantum curve of this vector bundle is 0, or equivalently that the further Narasima slopes of this vector bundle are positive. I never know the way this goes, the sign, but these are equivalent conditions. And one remark I want to make, that if D, so that was the question just before, if this data D is admissible, then we have definitely a cyclic object, acyclic associated vector bundle. In fact, it's semi-stable of slope 0. So, so this is a weaker condition. And so what is an example of small? A simple example of small are the simplest first we treated are Stein varieties with this property, finiteness property. So for example, naive interiors of affinoids or something like that. Then things which are compactifiable or compactifiable, is that the word? Compactifiable. That is analytic. So for example, if you take a proper variety and subtract a smooth closed set variety, you should get something of this form, and it should fit in this. We have it satisfies this theorem. We don't know about all quasi-compact varieties, quasi-compact varieties, whether they possess property.
Does the definition of small include quasi-compact?
No, that's what I'm saying. I don't know. We don't know whether it's total or quasi-compact varieties. We thought we had a proof, but there is a gap, and we were not able to fix it.
Sorry, but the small implies quasi-compact?
No. I mean, Stein variety.
I see.
No. Yeah. So that's all. Thank you.
Any questions for
So you guys, in the case of small, like even though it's not proper smooth, you still have this comparison between semester or PSC and P-adic.
Oh, yeah, I didn't mention that I ran out of time, that in fact you do get a comparison theorem, but you have to you have to derive everything. So where here you take yeah, so you cannot do it in this naive way. You have to take, so the Hodge filtration is derived filtration. Okay, so you don't take the image, you don't have the generation of the Hodge de Rham spectral sequence anymore. So you have to take just the argamma of the Rham complex, the whole of it.
So in particular, this D is regarded as a divided This D.
These yeah, that's right. So this is going to consist of the Rham cohomology, which is generic, can be generic cohomology, but the filtration is HI derived filtration. Okay. So it doesn't inject into the, and then you can, that's the difficulty here. The main difficulty here is not the Frobenius thing, because that you can understand. It's the actually topology on the coherent cohomology coming from this truncated filtration. Yeah, that's the main difficulty. And the comparison theorem has to take this, so it's kind of the yeah, I don't understand, but there is a comparison theorem, but it's not this. So could you speak up?
Oh, yeah. Could you say a bit more about a Claudette plots in the proton topology itself? Like, for example, in the state.
The further part comes from the Rham complex. So so you use P-adic computations of P-adics nearby cycles. So we use symptomic methods in our arguments. And you relate that to symptomic cohomology. And symptomic cohomology it can be written as some kind of mapping fiber of the Hilbert-Kato cohomology. And maybe you have to take some invariants here. Maybe you have to let me do periods as well. And then you have the Rham cohomology. So be the Rham plus cohomology actually. And then you model by filtration, derive modeling out. So this is what the cohomology is computed by, and this part is a part which resembles classical theory, more or less, morally speaking, and this is the part which contributes the analytic parts. But it's not as simple as that because in fact this arrow also kills a lot of here. So you have so this part which survives. This part which survives is not just coming from this, but it's also killed by a lot of Frobenius data here. And what survives is what you see here.
Yes, sorry, like a priori from that complex, it's not clear there's anything surviving that spot.
Why? I'm actually said because no, well, when I looked at it first, I thought that in fact a lot will survive, but less survives than I thought it would. So my intuition was the opposite.
So are your interests in this question? Do they come from just general foundational geometrical questions, or do you have secret or not so secret ideas to kind of?
Yeah, right. So no, I mean we actually went the other way because we were wanted to compute, you know, the cohomology, P-adic cohomology, cohomology of the covenants of the Greenfield power. And we started to compute it, and then we realized that these old methods, symptomic methods, to our surprise, actually work, give us what we want. So we wanted to have this to compute the P-adic cohomology and how we compute it. So that's the only thing we found.